be talking about imitation learning, the structured prediction view. View of structured prediction, sorry.
Yeah, okay, so thanks for coming. Thanks to the organizers for inviting me and doing all the organizing and stuff like that. So I'm going to talk about structured prediction stuff, which is basically what I do. So I'm a natural language processing guy, like, at heart. And I think to a large degree, natural language processing really is the field of structured prediction. Like, it's something that we've been studying since, I don't know, the 60s or something like that, with finite state methods and stuff like that. So that was sort of the culture that I grew up in, but I think things have changed a lot. And so I want to talk about sort of this relationship between imitation learning and structured prediction. But just to make sure we're all on the same page, I want to start out with some examples of structured prediction. And so I might go back and forth between calling it structured prediction and joint prediction, where I'm really just trying to predict a bunch of variables that are correlated, and I want to predict them sort of to optimize some joint loss or something like that. So probably the classic example of structured prediction is sequence labeling. So you get an input like the monster ate a sandwich, and you want to assign part of speech tags to the sentence. You also have things like named entity recognition that look very similar. Although actually, I traveled to Berkeley on Monday, not yesterday, but you also have other sequencey-like problems, like this is a DNA splice site prediction problem where you have DNA sequences and you're trying to separate them into, say, like introns and exons. Right, so these are all sort of sequencey problems. There are also more like tree-like problems. So in NLP, we love parsing. So this is a particular parsing formalism called dependency parsing, where you try to draw a tree over the words in a sentence to explain their syntactic structure. There are other problems, like in computer vision, where you might get like a 3D point cloud of voxels, and you're trying to label them as to what's a tree and what's ground and what's building and stuff like that. So what do these things have to do with each other? Well, we're trying to predict the values of multiple variables simultaneously. And we believe that there's some correlation among them. So in language land, we might believe that determiners precede nouns in English, or that sentences have verbs, and we might want to express these as features in our model. It could also be because I have a loss function that forces me to pay attention to structure. So the example I like for this is I don't know, I might be teaching a bunch of undergrads, and maybe in the first half of class, when I teach AI, the first half of class is basically graphical model stuff, and the second half is basically reinforcement learning stuff. And I'm going to give them an exam at the end of class, and it's going to cover both parts. And there could be two ways I score this exam. So way A is your score on the exam is your average across these two parts. That would be the normal thing to do. Way B is your score on the exam is the max of your score on these two parts. Right? And so if I tell you that your loss function is A, you're going to sort of study everything equally. But if I tell you your loss function is B, you're going to decide which is easier, and you're just going to study that half. And so this doesn't actually require the two things to be correlated, right? It could be the first half was on reinforcement learning and the second half was on ancient pottery. But because of how I've set up the loss function, you want to pay attention to the fact that there's interaction among these variables in terms of how you're being evaluated. So what's the classic way of sort of solving these things? So the classic way is basically graphical model-like things. So CRF, structured SVMs, and so on. So we have some input X, we have some candidate output Y, and we're going to score this thing using a linear function, or nowadays you're going to score it using a neural network. So the way that you define features here is you define a Markov random field. And there are lots of things that make this hard. So how do you deal with loopy structures? So if you're in a loopy BP type setting. What else? It can be slow to do inference in these models. And in order to get these things to train, you need to sort of assume that the loss decomposes over the same structure that your features decompose over in the MRF. This is my sort of hand-wavy model of how the classic approach works. So we're going to learn this score function that assigns a fidelity to input-output pairs. So good pairs should get a high score. And then at test time, I get some input, and I have to solve this argmax problem of finding the output that maximizes that score. So this is some sort of combinatorial optimization problem. Under like super restrictive assumptions, you can solve it exactly, often with dynamic programming or some form of integer linear programming. But in most cases you can't, and you have to do some heuristic search, and this is kind of unfortunate. So at the end of the day, these things are really, oh, actually I'm going to skip this example. So at the end of the day, these things are really slow. So why is this? So if you're talking about parsing, the number of trees you could possibly output is exponential in the length of the input. If you're trying to do translations, say from a foreign language into English, the number of possible translations is also exponential in the size of the input. Same thing if you're trying to do summarization. So pretty much anything you want to do, the number of output structures is going to be exponential in the size of the input in some way. And so you can sort of hope that maybe you do dynamic programming. This works if your features are simple. So if you're in a sequence labeling land, if you assume like Markov features, so things only depend on their neighbors, you can do dynamic programming. If you're in a tree space like parsing, if you assume like context freeness, you can do dynamic programming. But I think that one thing that like the past, I don't know, my whole life as a researcher has taught me is that getting better features is really a good idea, even if it comes at the cost of making inference harder. And so I'm really not willing to give up on good features, even if it means I give up on say, my favorite dynamic programming algorithms. And then the other thing that's often buried in these sort of results is that, like, yes, parsing under a context-free assumption is cubic in the length of the sentence, but there's also this grammar constant that sits out front, and often this grammar is huge, and it's often like the dominant cost in like real implementations of parsing algorithms. So that's sort of my like whatever 5-minute background on what is structured prediction and why it's hard. So I'm going to talk basically about 3 related but not super interconnected problems. So the first thing I'll talk about is the structured prediction is imitation learning, which is going to sort of set the framework to talk about this hidden expense of features. And then finally I'll talk about learning under bandit feedback. So that's the structure. You should interrupt me at any time that something's not clear. Okay, so we have this structured prediction problem, right? So we have some input x. At training time, we have some ground truth y. It belongs to a very large set of possible y's for this input. We have, oh, I guess I have pictures of this. So I have an input like I can, a can. The ground truth is pronoun, modal, verb, determiner, noun. I have this giant set of possible outputs. I have something maybe that my model is predicting, which I'm going to call y hat. I have a loss function, which tells me for some ground truth y and some predicted y hat, how good am I doing? And then, like usual, I have data sampled from some distribution. And so, you know, like most things, the goal is to find some predictor that produces outputs that belong to the correct output set. So for instance, if I'm trying to predict trees, the thing that comes out had better be a tree. And I want to minimize my expected loss on future data by learning this function h based on my samples. All right, so the way that we're going to do this, which is like very different from sort of the Markov random field approach, is to decompose things into a sequence of decisions. So how you do this is sort of your choice. The way, you know, the most standard sort of obvious thing for a sequence labeling task is to go left to right over the input. So I have something like I have a decision point, I choose an action like pronoun, then I have can, then I have another decision point, I choose an action like modal, and then I proceed through the sentence. And then at the end, I get to this final state, and I can look back at my path, and from this path, I can extract my full output. And then that thing I can score with my loss function. All right, good? Okay, yeah, so that's what I just said. Okay, so we're going to talk about this in terms of policies, because this starts to look a lot like reinforcement learning. So in general, a policy is going to be a function that I'll call pi, which maps observations to actions. So the observations can be the full inputs, the sentence I'm trying to tag, the time step I'm at, the previous decisions that I've made, so I can include all of them, and basically anything else I want as long as it's not from the future, right? It can only be from the past. And then this thing is going to choose an action, which is going to guide me through this, this decision process. Okay, so I'm going to now switch to this analogy for playing Mario, because this is a good imitation learning example. So here we have Mario. We're going to extract features from a grid around Mario. And then we're going to map this to one of 2 to the 4th possible outputs. So this is the buttons that you're pushing on the controller. And the key thing that I'm going to assume is that I have access to an expert. And I can watch this expert play a bunch of times, and I can try to mimic their behavior. So the analogy here to the structured prediction case is that in the structured prediction case, at training time, I have ground truth outputs from which I can reverse engineer maybe an optimal sequence of actions. Here's an example of an expert playing Mario. So this is, so Stefan Ross made this video. It's very nice. So the expert is very good. This expert is actually just a breadth first search algorithm, so it's very, very good. It's way better than any person would ever be at playing Mario. Okay, so we have training data that looks like this. And so the obvious thing that you can do is train a car. Oh, so now I'm switching from Mario to cars, sorry. So I can't draw Mario, I can draw cars, right? So I can look at the trajectory that the expert took. And I can construct a data set where I have the states that the expert visited, or the observations at each point in time, paired with the action that the expert took. So I'm going to call the expert the reference. So now I can train a classifier on this data set. Okay, so does this work? John knows the answer. It's 50-50. Okay, I will show a video, and then you will tell me. Oh, and then we're going to let Pi play, right? Okay, so here's what happens when you do this. Okay, so it does not work. So why doesn't it work, right? And so in particular, why does Mario get stuck behind the pipe?
Because the expert never ran into a pipe and had to jump over it.
Yeah, so the expert never got into this situation where they were right next to a pipe. And so Mario learned that in general it's good to run right. And so he's like, well, I'm just going to keep running right, even though I'm stuck next to this pipe, right? So we somehow want to be able to learn to recover from our errors. Okay, so I have this nice analogy to kittens. So I see that machine learning people like kittens. It's half of the deep learning papers are about kittens. But there are other kittens from 1936. So there's this nice paper by Heldon Hein studying 2 kittens. So they took kittens. They put them in this little box. And one of the kittens could walk around. And then the other kitten, their actions were constrained by the action of the first kitten, right? So the first kitten is basically controlling the second kitten. Okay, so they're seeing exactly the same thing, and then you basically look at how they learn about the environment, and the Heldon Hein result is that this kitten ends up awesome at interacting with their environment. This kitten, which sees exactly the same things, cannot learn to interact with their environment at all. So somehow actually interacting with the environment seems important, at least for kitten learning. And so maybe it's also important for I was going to say human learning, but machine learning. Okay, so how are we going to try to get around this? So we're going to try to learn to recover from errors. So we're going to start off the same way. We let the expert drive the car. We collect a data set exactly the same way we did before. We train a policy, which I'll now call Pi1, on this data set. And now we're going to let Pi1 drive the car, right? So Pi1 is now getting stuck next to pipes or whatever error it is that Pi1 makes. And now we're going to ask the expert at every state visited by Pi1, what action would you take in order to recover from that error? So you should think of this as I have this poor person sitting in a car that's driving itself, and the person is frantically trying to steer the car back onto the road, but the car is ignoring what they're saying. But it's recording their actions so that we can learn to recover from errors. So this gives us a new data set, which we'll call D1. We take the union of these two data sets, we train a new policy, and then we run pi2, we collect expert actions on pi2, and we repeat this process. All right, so this algorithm is called Dagger. It's like one of my favorite algorithms. It has a nice result that it's not my algorithm, so I can say it's my favorite algorithm. It has this nice result that basically, like, I'm going to sort of hand wave over the exact details, but basically what we say is if the classifier for predicting the actions has an error rate of epsilon, then the total loss of the policy is going to be bounded by something like t times epsilon plus a little constant. And so the reason you should be impressed with this is because it essentially means there's no compounding error. So I'm making t many decisions. On each decision, I suffer epsilon error. And so the best I could really possibly hope for is t times epsilon. And I'm basically getting this plus a small constant. Right? So the supervised algorithm that doesn't work, that gets stuck next to a pipe, you get something like t squared epsilon, and that's because of compounding error. Okay, so does this work? Yeah, it works a lot better than supervised learning. I can show you curves rather than videos, but videos are more interesting. So it's not perfect, but it doesn't have these degenerate problems like getting stuck next to pipes. Okay, so I thought this was going to end by now. It will end eventually. So we take this same idea and we apply it, instead of to playing Mario, to doing sort of structured prediction tasks. So I'm going to go over the structure. Please be done. Okay, I'm going to go over the structure one variable at a time, and I'm going to predict each one. But importantly, at training time, I'm training to recover from my previous errors so that if I get off path, I don't lose. So does this work? It actually works quite well. So this was a paper we had at NIPS last year, although I think it was first rejected from NIPS 2014, so it's like a little bit out of date. But basically, this is comparing the imitation learning style algorithms to more classic algorithms like conditional random field, structured perceptron, and structured SVMs with varying training algorithms. And so here, the x-axis is the amount of time that it takes to train. Y-axis is accuracy on test data. So this is what you get if you ignore structure. So you just make every prediction independently. So you train very quickly, but you plateau pretty low. If you do the imitation learning stuff, then after about 10 minutes, this is on 1 million words of training data. So after about 10 minutes, you have basically what was at the time a state-of-the-art part of speech tagger, and was substantially faster than, say, various implementations of CRFs, which I guess are here and here, and also structured SVM and stuff like that. So I think the main result here was that we get something that trains super fast because we don't have to do like belief propagation or dynamic programming at training time. And it also works really well because it learns to sort of recover from its own errors. Yeah?
Do you need to sort of do several iterations of this process? Or?
Yeah, so the one thing that I guess I'm hiding from you here is that the algorithm that I described was really very batchy. But the algorithm we're using here is much more online. So what we're doing here is, well, you can basically just think of it as a batch size of 1. So we get a single training example. We run the current learned policy on that example and collect the corrections at each point in time, and then do an online update to that policy. Yeah?
Where do those corrections, or is it still a human?
Oh yeah, so that's a really good point. I should have had a slide for this. So the corrections are algorithmic. So the setup is basically, I'm at some state. I wish I had a, oh, there's a board. That's awesome. Yeah, so I've gone along for a while and I get to some state S. And then what I'm trying to compute is pi ref of S, but it gets to cheat and it gets to look at the ground truth because it's training time. And so this should be the action that if I took that action and then played out the rest of time optimally would minimize the long-term loss. So it's not very pleasant how to write this, but we want to minimize the loss from the truth to this predicted y hat, where y hat is reached from S, right? So we want to sort of roll out to the end until we have some loss. And so for most, not for most, for many loss functions, you can do this in closed form, and it's convenient. Okay, so you can, the other thing that's nice is we had this nice way of like writing code for this. So if you want to play around and write your own structured prediction problems, you can do this very easily. So this was the version that was in the NIPS paper last year. We also had results on named entity recognition and dependency parsing, and they look sort of qualitatively the same. It's also very fast at test time. So now everyone might be sitting there like, but like how? What about neural networks? So everyone does neural networks these days. So I think one thing that's actually quite interesting is that this like sequential prediction view of structured prediction is essentially the standard view in neural nets land. So people who do structured prediction with neural nets, they basically decode with recurrent neural networks, which look exactly like make a prediction given a state, move to a new state. Make a prediction given a state, move to a new state. So it's exactly the same model. If you want to play around with it, so we built this, this thing called Masarico, which is built on top of PyTorch. So it completely separates tasks like part of speech tagging from the neural network features you want to implement, from the learning algorithm like Dagger or maximum likelihood or reinforce or anything like that. So this is with Tim, who's at Hopkins. It's not actually out yet, but it'll be out soon. So if you don't want to worry about tasks and neural net features, but you have some new imitation learning algorithm you want to try out on like a battery of NLP problems, this should make your life very easy. All right, so that was the first part. So I want to talk, so that's sort of addressing this question of, oh yeah, John.
Going back to the previous slide. So with the neural networks, one of the things that they're doing is you're kind of carrying over a lot of internal state from step to step.
Yep.
This is being handled here?
Yep.
Okay.
So the thing that's tricky is to figure out how to do the backpropagation right.
Yeah.
It's not totally trivial. Oh, and in case you're wondering, so Masarico is Portuguese for blowtorch, which is, okay. Anyway, I also learned that you're not allowed to have cedillas in URLs, so please don't call it Macarico, even though that's what it looks like. Okay, so this part is really addressing this computational problem of making structured prediction efficiently, sort of from the algorithmic perspective. But there's another reason that structured prediction is often expensive, and that's because features are expensive. And so what I'm going to talk about here is basically trying to get around the fact that computing features in structured prediction models can often be like a huge bottleneck in terms of computation. So here's sort of the view that we had. So this is how like NLP works. So we get some training data. We go talk to people in this room, and they tell us what their favorite learning algorithm is. And we train, and we get a slow predictor. So we're not very happy with that. So we spend a bunch of time building some heuristics, like A-star heuristics or something like that, to try to make this fast. And so what we were really trying to do is glue all of these things together into one piece that's just the learning algorithm, right? So basically, like, can we learn to both be accurate and efficient? Right, so the quality measure that we care about is some trade-off between speed and accuracy. So I'm going to give an example from dependency parsing. So we have a sentence like NLP algorithms use a kitchen sink of features. We're trying to construct a tree that says, for instance, that use is the head verb of this sentence. It has a subject, which is algorithms, and has an object, which is sink. And then the rest of the tree sort of builds out from there. So how do people, or what is one way that people do this? So one way that people do this is they think of it as a minimum spanning tree problem. So we have a big graph that's fully connected. There's a unique node, which is the root, and otherwise all of the nodes are words in the sentence. And there should be actually, there we go, there are the words. And so any directed spanning tree of this graph corresponds to a parse tree of the sentence. So in particular, that's the gold standard tree. Okay, so how does learning work here? So we throw a bunch of features on the edges, or if we're in neural nets land, we let a neural net build up features on the edges. And then this will give us an edge weight for every edge in the graph, where depending on whether you're minimizing or maximizing, large weight edges are good and small weight edges are bad. So if you actually want to run this at test time, the first thing you do is you compute some part of speech tags. The next thing you do is for every pair of words in this sentence, you compute some features that talk about how related those two words are. And then you run directed MST. So it turns out that running directed MST is actually quite fast. And that computing features is way, way slow in these problems. So this is sentence length versus time. So the blue bar is how long does it take to do the part of speech tagging. That's quite fast. The yellow is once you have all the features, how long does it take to run directed MST. That's also very fast. And then the orange is how long does it take to compute these pairwise features between every word. And that's incredibly slow. So this is an average length sentence. And for that average length sentence, something like 300 times as much time is being spent computing features as running MST. So this sort of suggests that, like, going out and finding better MST algorithms is not going to make this much better. We really need to get this bar down. So how do we do this? So basically what we want to do is we want to only compute features that are actually useful for predicting the final tree. Right? So there are going to be lots of features that don't really contribute. But we don't want to do like offline feature selection, because we want to be able to like choose more features on edges that are hard and choose fewer features on edges that are easy. And I'll show you later that that actually helps. So the way that we're going to do this is we're going to start off with a graph that has almost no features on it. And based on this graph, which should be easy to, or should be efficient to construct, I'm going to run my, my parser. Right? So this is basically a free operation. This is going to produce some parse tree of this sentence. So now I'm going to go through every edge in this parse tree, and I'm going to decide, do I want to lock that edge? Like, do I believe that that edge is correct? Or should I leave it as sort of like, I'm not sure? Okay, so for instance, I might, so this is going to be done by a classifier. My classifier might be sure that this edge is correct, but unsure about the rest of the blue edges. So side note, it's super important that you only look at the blue edges and not every edge. If you look at every edge, you're now paying n squared and you lose. So the reason why you want to run the parser over and over again is so that you only look at a subset of the output at each step. Okay, so now for all of the non-locked edges, we add, so we throw out ones that are inconsistent with this edge. And then for all of the remaining edges, we add some more features. All right, so then we run our parser again. It produces a different tree. We lock some of the edges. Oops, I thought there was more animation. We lock some more of the edges, and then when every edge is determined, or when we've exhausted all of the features, we stop. Okay, so does the algorithm make sense? Okay, so this is basically a control problem, and I've already told you how to solve control problems. You run Dagger. So we run a small variant of Dagger that we call coaching, but it doesn't really matter. You basically run Dagger on this problem to learn how to control this, this edge locking mechanism. So the first thing we looked at was how does this compare to static feature selection, right? So I'm just going to decide ahead of time which features I'm going to compute on all edges and then always compute those features, versus doing it dynamically as you build up the tree. And so here on the x-axis we have runtime, on the y-axis we have accuracy. And so, yeah, it's better to do it dynamically. So the other thing that's kind of interesting is looking at what actually happens over time. So there are a bunch of lines in this graph, but so the x-axis is how many features have we added so far. And then the y-axis is going to vary depending on what line we're looking at. Okay, so the gray line is how many edges remain. And so the first thing that sort of happens is that this drops off quickly, which means that lots of easy edges are being locked in quickly. The second thing that's interesting is that, let's see what's the right way to say this. There are edges that stick around until the end because I'm very unsure about them, and adding those features does actually help resolve them, right? So the message is that for easy edges, you don't need many features and you can win there. For hard edges, you actually do need all the features and you can still win there. Okay, so if you were a parsing crowd, you would want to know what my unlabeled attachment accuracy scores are. I think people here maybe don't care so much. But basically, the thing that you want to look at is the baseline, which is the ugly yellow color, and our thing, which is green. And this is over a bunch of different languages. And so sometimes we're better than not doing feature selection. Sometimes we're worse than not doing feature selection. But the y-axis is like super squished. So really, it doesn't make a huge difference. Like, we don't do better or worse at parsing. We just get faster. In terms of speed, so on English, this is all normalized to 1. So on English, we're about 5.5 times faster than the baseline. For Chinese, we're not really that much faster. The blue bar is this vine pruning algorithm by Sasha Rush, which is quite different, but it was sort of the obvious competitor at the time. Okay, so I told you this story for dependency parsing, but you can actually do this for almost any algorithm where you have some prediction task that's making internal decisions that you want to control. So we also did this for ILPs. So a lot of structured prediction problems you can write down as integer linear programs, or actually probably all of them you can write down as integer linear programs. And then you can solve those using like branch and bound or something like that. So I will not explain how branch and bound works. The important thing is that you're basically exploring the search tree and you're maintaining little bounds on the values at each point in the search tree. And you want to prune edges and explore the tree in an interesting way. And so if you look at like well-engineered ILP solvers like Gurobi or Cplex or something like that, they have like decades of human effort into designing heuristics for when to prune parts of the tree, what parts of the tree to explore next, and so on. And so we can apply basically the same idea to exploring the to exploring the branch and bound tree as we apply to exploring the dependency parsing tree. Yeah, so that's basically what I said. So I think I will just tell you the take-home story. So we compared against Gurobi, which if people haven't used, Gurobi is awesome unless you're trying to beat it. And then you hate it because it's actually really, really hard to beat. Depending on the problem that we were looking at, we could either get essentially 0 improvement or like reasonably substantial improvement over Gurobi speed. But I think like, 1.5% better doesn't sound that great, but getting any improvement at all was like a major uphill battle. Gurobi is like super, super well engineered. Okay, so you can do this for lots of problems. And now basically anything that you can cast as an ILP, you can use this same idea to try to speed up. All right, so are we good for that? All right, so last thing, I will not use Dagger here. So this will be the non-Dagger part of the talk. So I want to talk about structured prediction under bandit feedback. Oh, there are supposed to be edges here, but okay, so what's the setup? So I'm like some web page, and when someone goes to my web page, I have to decide like what stories do I want to display, how do I want to orient them on the web page, what size font do I want to use, what color do I want to use, what images do I want to use, and so on, right? So I have this big design problem, and I'd like to learn to make better designs based on looking at user behavior. So I'm going to think of this design problem as a structured prediction task, right? So I have a bunch of variables that I'm trying to predict, and once I've made predictions for them, I have some web page layout software that's going to generate a web page for me, and so I want to pick those variables to optimize some like user metric. The important thing, and the thing that's different from everything I've talked about so far, is that I only get to try once. Right? So like someone goes to like Le Monde, I don't get to say like, here are 10,000 ways I could have laid out this web page, which one do you like best? Right? So I get to show them one, and I get to see like, hey, do they stick around my web page or not, or however I'm measuring performance. So this is very much like a bandit feedback-like problem. The world gives me a context, which is like the user who came to my web page. I have to make a prediction over a bunch of variables. And then this gets shown to the user, and the user gives me some reward. And then tomorrow, some new user comes. OK, so this is structured contextual bandits. So how does this compare to sort of the structured prediction case? So we're going to think about the states, the search space, in exactly the same way. So we have a bunch of variables. We're making decisions. We're exploring the space. The feedback is very different. So before we get full labels from which we can play games like this, here we just get to make a single prediction and collect a single loss. So traditionally, in sort of the structured prediction view of the world, we assume that our reference is optimal. So in particular, I can solve this problem optimally. This is definitely not going to be true in the web page design task. So in the web page design task, there's some software that's running on Le Monde right now. And it may be good, it may be bad, who knows? But I would actually like to improve on it, right? So like if all I give you at the end of the day is something that's like not much worse than the reference, this is like not so useful to me. The reference is only available at training time in the supervised case. In the contextual bandit case, we're going to assume it's available both at training time and testing time, so I can always run the off-the-shelf algorithm. And so like I said, the goal is sort of very different. So in the structured prediction setting, the goal is to imitate the expert, to imitate this thing. But in the contextual bandit case, the goal is to improve on it. Right, so and I said this before, but existing algorithms like Dagger can give you a result that like your loss is not much worse than the loss of the reference, but this is not useful in the contextual bandit setting. Okay, so there are two things we need to do. So we need to be able to learn a policy that improves on ref, and then we need to be able to do this under partial feedback. So I'm going to spend most of the remaining like 5 minutes talking about this first one, and then I'll just sort of hand wave on the second one. Okay, so one question is, what do I want to do? So trying to figure this out is kind of tricky. So we would like to still be competitive with the reference. So if the like current web page layout on Le Monde is optimal, I'd like to still be optimal. Right? So that's certainly something that I would like. Maybe I would also like some notion of local, okay. I would really like global optimality. I will tell you now, you're not going to get it. So I might prefer, or I might like some form of local optimality. And the notion of local optimality we'll use is that we compete with our own one-step deviations, which basically means if green is the decisions that my current policy takes, then a one-step deviation of green is something that makes one decision differently from how green does. And I would like green to be locally optimal in this neighborhood. Okay? All right, so we're going to think about 3 things in our algorithm. So we're going to have a roll-in phase, and then we're going to try some sort of deviation, and then we're going to have a rollout phase. So the main thing that matters is that how we roll in affects the distribution of states that we train on, right? So this is like the Mario getting stuck next to a pipe case. The rollout affects how we score actions, right? So I'm at some state, I have a bunch of actions available to me. Which one is best depends not just on that action, but everything I do in the future from there. And so the rollout affects how we get scores. Okay, so the first thing we did was sort of, I guess, a bunch of like lower boundy-like things. So we looked at different ways that you can do roll in and roll out. So you can roll in with the reference policy. So this is like getting stuck next to a pipe. You can roll in with the learned policy. That's much more like Dagger. You can roll out with the reference policy. You can roll out with the learned policy. And you can roll out with like a 50-50 mixture of the two. So if you roll in with ref, you get an inconsistent algorithm. You basically, read this as you get stuck next to pipes. Yeah, I mean, why does this happen? I mean, it basically happens because the states that you're trained on are not representative of the states that you test on. So if you roll in learn and then roll out with reference, then I can't guarantee that you get local optimality. And basically the reason why is because if ref is not realizable, then rolling out with ref might be sort of overly optimistic, right? You might think like, oh, I can get there if only I take this action, but then you actually can't learn to sort of follow the right path. If you roll in learn and roll out learn, you're not using ref at all, and you're just doing reinforcement learning, and reinforcement learning is hard, and so we don't want to do that. And so it turns out that rolling in with the learned policy and rolling out 50-50 is actually a pretty good thing to do. So we call this particular algorithm lols. So the main result that we get is that if you run this training procedure, the regret of the learned policy is bounded by the sum of these 2 terms. So the first is basically, sorry, let me say that differently. So these 2 terms are small. So the first term is what's your regret with respect to the reference, and the second term is what's your regret with respect to your own one-step deviations. And so we would sort of like both of these to be small simultaneously. We don't have that. We have that the sum is small. So there are a couple of things that fall out of this. So the first is this term is always non-negative, which means that this term is always small, which means that we're guaranteed to compete with ref. So that's good. The second thing is that if ref is already optimal, then this is non-negative. And this means that the red term is small, which means that we're locally optimal. And then the third thing is that if ref is suboptimal, which is the case that we care about, then one of 2 things happens. Either we're locally optimal or we're better than ref. And so this is not like super clean, but basically the result is that in the case that we care about, we either improve substantially on the initial policy or we're at least locally optimal. Okay, so getting exact local optimality is hard. I won't talk about that. Does it work in practice? Yes, it works in practice. No one wants to know results. Okay, so I think the main thing is that, right, so in the case where the reference is optimal, the thing that should be good according to the theory is still good. In the case where ref is suboptimal, which is the case we care about, then lols is much better than everything else. So in a sense, the empirical results match what the theory says. Okay, so can you do this with bandit feedback? Yes, you randomize, and then you do importance weighting, and you can ask me afterwards how to do that. So I should say this is like work with lots of people. So in particular, most of the stuff is work with He, who's a postdoc at Stanford now. She'll probably be on the job market next year. You should totally hire her. She's awesome. And also, if you're really interested in sort of like the theory stuff, so Stefan was one of Drew Bagnall's students. His thesis is awesome. So if you're looking for a place to get started with some of the analysis stuff, that's a really, really good place to look. So this is basically what I said, and I will stop and take any last minute questions.
Any questions? Okay, well.